Hello and welcome. In this video, I'm going to discuss some of the data analysis steps for experiment 2, the enthalpies of sublimation of some different types of compounds. And so one of the key equations that we have is equation 13. Equation 13 allows us to calculate the vapor pressure of a substance by the experiment where we determine the mass loss of a compound. That's this little M symbol here. This is related to this beta term here. I'll talk about that in a second. The area of the pinhole, capital A, the time, how long we allow the experiment to take place, and then the ideal gas constant, the temperature, and the molar mass of the substance. Now, there are 5 variables here that we're experimentally determining throughout the experiment. That would be the mass loss, beta, the area of the pinhole, the time of the experiment, and of course the temperature. So from these 5 variables, we should be able to calculate the vapor pressure. Now, let's talk about pressure for a moment. Pressure corresponds to a force exerted onto some sort of an area, and we can think of the force as a mass that's accelerated onto a surface. And so you might think of your SI units here as mass times acceleration divided by the area that they're sitting on. And so if you're thinking of the units here for pressure, that will define the SI unit of Pascal. So 1 Pascal, the SI unit of pressure, is going to be our unit of mass, a kilogram, and then our acceleration, meter per second squared, and then dividing by the area in SI units meter squared. And so that's going to lead the units of the Pascal to being 1 Pascal to being 1 kilogram meter to the -1, second to the -2. Now, the reason why I'm going into the units here is because we're going to have to put the units for our variables for these values that we're measuring in the lab and the molar mass in the proper units so that we can actually get some unit out of pressure that we're accustomed to working with, such as the Pascal, the SI unit of pressure. And so if we plug in our mass loss in kilograms, our area in meters squared, our time loss in seconds, our temperature, and our ideal gas constant, of course, in units of Kelvin. Even our gas constant, we're going to want to use the joules per mole Kelvin units for our gas constant, where the SI unit of energy, the joule, is a kilogram meter squared per second squared. So you see these fundamental units here showing us that we want our molar mass to be in kilograms per mole. So you just look up your ordinary molar mass, use enough digits on it so that it's not limiting the error in your experiment, and just use the molar mass in units of kilograms per mole. Okay, so you go into the lab. You've already done this, or hopefully you've already done this. You set up your sample for a certain amount of time. You record that time precisely so that you can have some sort of a knowledge of what the time is. It doesn't matter what the time is, just whatever it happened to be for your experiment. You're going to measure the pinhole diameter, and then from the diameter calculate the area. Let's talk about that calculation for a minute. So we're calculating the area of our pinhole by simply pi r squared. You're actually measuring the diameter. You might think of this as pi d over 2 squared, and you can work out the arithmetic on that to calculate the area. In a later video, we'll talk a little bit about the error analysis that goes along with this equation. Using this form here might help you with your error analysis and simplify that a little bit. And then the last term here is this beta term. Let's talk about this. Beta has a relationship to how thick this orifice is that our sample is subliming from. And so if we think of a cell that has a relatively thin orifice versus a relatively thick orifice, what this beta term is calculating is what's the probability that a molecule is going to strike that pinhole surface and then deflect back into the cell. And if you imagine 2 different types of cells, you have a cell with a very thin orifice versus one with a very, say, thick orifice, the difference is going to be you're not going to get as much mass to come out of the cell with a thicker cell. And beta is going to be the term that allows us to calculate a proper vapor pressure given whatever the particular dimensions are of our cell. So the key terms for beta are the L over the D. And so the L term is the thickness, and the D is, of course, the diameter. And so the L to D is the thickness to diameter ratio, And so you can imagine that as the cell is thicker, more material is deflecting back into the cell. Beta is really just a probability of escape. If beta were 1, it just means 100% of the molecules striking the orifice are leaving the cell. That's going to be true for a cell that has a very, very thin, as the thickness of the cell is approaching 0, is going to lead us to a beta of 1. And then, of course, we're going to lead to a beta of 0 whenever the cell has an orifice that's really, really thick. So in our case, if you look later ahead a couple pages, you're going to get the thickness. We've tried to measure this before in the lab. It's kind of tricky because it's so thin, but we'll just use the manufacturer's provided dimensions, and you can pick that up a little bit later in the handout. Use that as your thickness, and then use the diameter that you determine and measure in the lab. Okay, and so again, we'll talk about error analysis later with beta, but you plug beta into your equation here. The beta is usually, just so you get a sense here, it's usually around 0.997, somewhere in that range. So it should be about 99.7, somewhere in that ballpark. I don't remember exactly where it is. Maybe 99.5% of the molecules actually leave the cell. So I think we've talked about all the terms that allow us to calculate our vapor pressure. Of course, if we increase the temperature as you do more trials, you're going to be changing this temperature. Let's say we drop the temperature, then you should see a subsequent drop in the vapor pressure of our sample. So the last discussion point for this video is going to be these equations here on the next page of our handout. We have the Clausius-Clapeyron equation and equation 17 that we then integrate from either two different pressure bounds, P1 and P2. So we get a relationship that relates the vapor pressures of our substance to the two different temperatures that we might run the experiment at. So you can imagine running an experiment at temperature 1, determine pressure 1 at that temperature, repeat the experiment at temperature 2, determine the vapor pressure at temperature 2, and then what we can do is determine that, or use the equation in equation 19 that says that the natural log of P2 over P1 is equal to the negative delta H sublimation over R, and then the 1 over T2 minus 1 over T1. So this works perfectly fine if we do two determinations of the vapor pressure at two different temperatures. So this is the equation. Usually after 1 day of lab work, you've done 2 trials, you can plug your work into equation 19 and see how that works out to determine an enthalpy of sublimation. Another approach would be, well, why don't we integrate our equation across all pressures so we come up with a more general relationship, that is that the natural log of pressure is equal to negative delta H sub over RT plus a constant. And then what this allows us to do is take a plot of natural log of pressure versus 1 over T, and then that should yield a straight line where the slope is equal to the negative delta H sub, the enthalpy sublimation, divided by the gas constant. And so equation 21 works really well if you have multiple, if you have like 3 plus determinations. And if you have 2 determinations, equation 19 is the one that you want to use. Occasionally I see people take 2 determinations and plot the line and use the more general approach of equation 21. It's kind of weird to see a plot with 2 points on it because, of course, that has to be a perfect straight line. And one last detail that I think we'll talk about in a different video is we could also do what's called a weighted linear regression. Might force us to use a little bit more complicated of a fitting routine than available with Excel. But in a later video, we'll talk about how we might be able to do a weighted linear regression so that we can use the different errors in the vapor pressures that we determine to help us steer the line and maybe determine a slightly more precise enthalpy of sublimation. Okay, so that's the basic video today, is that hopefully you can calculate your vapor pressures following a couple of trials, and from that you can determine a enthalpy of sublimation for your compound, and then maybe later come back, do a couple more trials, and use a more general approach and hopefully obtain an even more precise value. Okay, thank you for the attention.